Hello everyone. Today let's solve the problem number 218, the skyline problem. So what the question states here, a city skyline is formed by the outer contour of buildings when viewed from a distance. That's what they have given here. A city skyline is formed by outer contour of buildings. So they have given here buildings, right? So a city skyline is formed by the outer contour of buildings when viewed from a distance. Each building is represented as left, right, height. This one is left, nothing but x-axis. This one is the right, nothing but y-axis. This is also x-axis. These both first two numbers what they have mentioned, this is x-axis. Suppose if we consider here 2, you can clearly see here x-axis. Just give me a second here. This one 2, this is nothing but 2 in this case. If I'm considering just this one here, 2 9, 2 to 9 here as 9, this one, this is x-axis, this is x-axis. I hope this is clear. And 10, this is y-axis, this is nothing but height. So this one you can clearly see 10 till 10, you can clearly see the diagram here, right? That's what they have shown here. So each building is represented by left, right, and this one height, where left is the x coordinate of the building's left edge. So we saw that one. Right is the x coordinate of the building's right edge. We saw that. And finally, height is nothing but the height of the building. I hope this is completely clear. These three steps. The question till here is completely clear. So what we have to do? A skyline is a sequence of key points. You can clearly see this is the skyline. What they have said. Just give me a second here. 1 second. Yeah, this one skyline I'm speaking of. A skyline is a sequence of key points x1 comma y1, x2 comma y2 until, so whatever we have, this one, the final edge. So whatever we have here, right? A skyline is a sequence of key points where each key point marks the start of the new height. Each this one here, you can clearly see this, the output here, what they have given, 210, 315, 712. This one, each key points marks the start of new height. Here this is nothing but 2 x-axis to 10 is y-axis here, 2 to 10. And this one, next one is 3 to 15. This one, 3 to 15, 3 they have started from x-axis here, 3 to 15, 7 to 12. Here you can clearly see this one, 7 to 12. And 15, 10, this one, 15, where is 15, 15, 10, this one, 28 and 24, 0. 28, this one you can consider here, 28 and 24, 0, the last one, right? So each key point marks the start of the new height. The last key point has an height 0. You can clearly see here, this one I'm speaking of. The last key point has height 0, marking the end of the skyline. Consecutive points with the same height must be merged. So here you can clearly see consecutive, this one, points with the same height must be merged. So this we have to keep in mind. Again, I'm telling, each key point marks the start of the new height. The last key point has height 0, making marking the end of the skyline. This we know. And the final one is important one. This one you have to keep in mind. Consecutive points with the same height must be merged. So I hope this is clear, right? These 3 points. So what we'll do now, let's initially discuss the approach. I hope the question is completely clear. The example 1 we considered, right? Same goes with the example. You can just try to visualize in the same way that I said for the example. Say example 1. Same goes with the example 2 as well. So I hope the question is completely clear. Initially, what we will do, this one. Let's discuss the approach first. Approach followed by edge cases one by one, and then third one, let's after discussing the edge cases, let's finally write the code and discuss the complexities of the code that we have written, right? Initially what we will do, let's discuss the approach. So let's discuss the approach step by step. Initially I have considered the first example, the same example that they have given in the question, right? The first example that I have considered. So we are going with the segment tree. We have to keep this in mind. We are going with the segment tree. This one we have to keep in mind. Buildings they have given here, output they have given here. So I hope this is completely clear, right? So I hope this is clear. The second one, let's start with the step 1. First, initially what we are doing, we are extracting the unique x coordinates. So we are extracting unique x coordinates. First, what we are doing, buildings introduced critical x coordinates. We are just considering the x coordinates here. So if I come here, just give me a second here. So for the initial step, we are just considering x coordinate, means first two this one numbers from this array, from every array we are considering 2 9 3 7 5 12 here. So this one 15 20 19 24, first two elements in the array. So that's what we are considering here, 2 9 3 7 5 12 15 20 19 24. So we will sort this one in the ascending order. So we are sorting the x coordinates, nothing but first two elements in the array. We will be sorting this one in the ascending order. So one thing, so here we are going with segment tree with sorting, right? So the time complexity would be, sorting will be dominant factor in this case. So time complexity would be n log n. You can just take this hint, right? So 2 3 5 7 9 12 15 20 and 24, this is after sorting. Let's come to the second step. This is more of a theory, this question basically. So let's go with the coordinate compression. When I say coordinate compression, what we are doing here, we are mapping x coordinate to the compressed index. So we are considering the x coordinates to the I mean, we'll map each x coordinate to the compressed index, this one to the compressed index. Why we are mapping each coordinate to the compressed index here? For the segment tree operations. So when I say segment tree operations, we are going with query as well as the update. So we have to update every step. Updation is required, and for the new height to occur, and also we are going with a query, only two functions within the segment tree, right? So we are mapping each x coordinate to the compressed index for the segment tree operations. So let me come to the step 3 here. In step 3, what we will do here, we will perform segment tree for the height updates. When I say height updates, we are updating heights in a range corresponding to the each building. That's what we saw in the output, right? So we have to update the heights in a range that is corresponding to the each building, x and y axis we have initially, if you remember in the question. That's what they have given in the new graph at the right side. So we will be going with a segment tree for the height updates, nothing but update heights in a range corresponding to the each building here. This is fine. Next, we will traverse all the x coordinates and query heights. We will be traversing through all x coordinates in the query heights. I hope this is clear. So the final step is, we have to build the final skyline. That one you saw in the right side, right? We have to build the final skyline with the new heights, right? Previously we have already discussed, we will traverse through the compressed x coordinates. If you remember, here we will traverse all x coordinates and the query heights, if you remember. So we will traverse compressed x coordinates. If the height changes compared to the previous height, if the height changes, then we will record that key point. That's what we will be doing. If the height changes compared to the previous height, then we have to record the key point. This is very important. So the final output will be here: 210, 315, 712, 12 0, 510, 28 and 24 0. After this one, after sorting and segment tree operations. So when I see segment tree operations, we are going with two things. One is this one, update, and another one is query, right? So I hope this is completely clear. This is it for the approach. This is the approach that we will be going with, right? So let's discuss the edge cases step by step. So the first edge case that we are going with here is this one, single building. When we have only one building, here we have 1, 5 and 10. Left x-axis, right edge of the x-axis, nothing but x-axis, right edge of the building, left edge of the building. This is nothing but the y-axis, right, y-axis or the height. This one left, this one right. This is height. You can consider left, right and height, right? So just give me a second here. Here in this case, output will be 1 comma 10 and 5 comma 0. Here when I say 1 comma 10 and 5 comma 0, so you can visualize in the same way that I had explained by considering the example 1 for the approach, right? So here this is for the condition single building. Let's move on with the second edge case, nothing but non-overlapping buildings. So for the non-overlapping buildings, here you can clearly see 1 2 3 we have 3 4 4. So if you draw it in the form of graph as shown with the x and y coordinates, this is non-overlapping. So I can just try this one. So the output will be in this case 1 comma 3 2 comma 0 3 comma 4 and 4 comma 0. This will be the output basically. This is for the second edge case. Next, let's go with the third edge case, nothing but nested buildings. So nested buildings means we will be having the nested structure, right? So if you can please do draw the diagram and just check if you want to check for the edge cases, right? This is for the nested buildings. Here the output will be 110 and 2510 I have considered within the array. The output will be 1 comma 5, yeah, 2 comma 10, this is fine, 5 comma 5 and 10 comma 0. So if you want to know about the output every step, you can just try it out in the same way that I showed for the by considering the first example in the approach. So this is the third edge case. The final edge case or the fourth edge case is same height consecutive buildings. When I say same height, all should be of every building should be of the same height, right? So it would be I have just considered this one 135 365 and 695. You can clearly see here height 5 5 5, right? Same height consecutive buildings. So the output here will be 1 comma 5 and 9 comma 0. So you can visualize in the same way as I have said earlier. So these are the four edge cases that we need to consider. First one I considered for sorry, just give me a second here. First one we went with the single building. Second one we went with non-overlapping buildings. Third one we went with nested buildings, and the fourth one that we went with was same height consecutive buildings. I hope all the edge cases are completely clear. Right now, let's start writing the code. So let's start writing the code here. The first step here is we have to extract unique x coordinates from the buildings and sort them. The first two elements we took and we sort them. We have to sort them, right? Nothing but here we are extracting unique x coordinates from the buildings and we will sort them. Here, let go. Odds. This one I'll just consider this one odds, right? This is fine. Let's make use of the spread operator here. Set. Let's make use of the set as well. Buildings. They have given here buildings. This one I'm considering. So first two elements we have considered. Let's sort this one. So I'll just make use of the flat map of any variable you can consider. I'll just consider b here. This one will be b of 0. This is fine, comma b of 1. I hope this is clear. Just give me a second here. Did I miss something here? So yeah, here bracket I have missed. One more bracket we should be having here. This is fine. This is fine. Finally, we have to sort this one, right? So let me sort this one in the ascending order. So we have to sort the first two values if you remember. So I'll just give here a comma b, a minus b. So this is fine. We have extracted the unique x coordinates, nothing but first two elements from the array, and we are sorting them from the buildings and we are sorting them. This is the first step. So if you remember, in the second step, I had said map each unique x coordinates to a compressed index for the segment tree operations, if you remember. So we will be making use of the hash map as well. So I'll just go with let map equals. Let's create new map of co dot map here. This one v comma I This one is fine. V comma I plus 1. I hope this is completely clear. So the next step here is what we'll be doing here. We have to map each unique x coordinates to a compressed index for the segment tree operations. So that's what we did here. So sorry, this one we have already done this one, right? So we have mapped each unique x coordinates to the compressed index for the segment tree operation. So now what we will be doing, we will be initializing the segment tree. By passing the length of the, we have to pass the length of the coordinates to the segment tree. Along with the, we have to store the result somewhere. Let's initialize the result as well. Also, we need the previous height, right? So these three things we will do here. And this step, let me come here. Initially, let's initialize the segment tree. I'll just consider SEG in this case. So I'll just give here segment tree coords length length of the coordinates. This one is fine. Result, let's initialize this one to the empty array. This one previous height, this one I'll initialize this one to 0. I hope this is clear, completely clear. So we have initialized the segment tree. As I have said previously, I have said this one multiple times. We'll be making use of two functions within the segment tree. One is update and one is query. So for that one, we have to build the segment tree from the scratch. Let's build the segment tree. Then let's make use of the two functions. One is query, one is update, and one is query within the main function. Right? Let's start building the this one segment tree. I'll quickly give here segment tree. This is fine, and let's make use of the constructor, or this is the initialization part. Let's pass in here. This is fine. N equals n. We are initializing this one to the n. Next thing is we have to initialize the segment tree to store the maximum height. So maximum height will go in this way. This is simple, man. I'll just give here this dot tree. Yeah, we are going with the array, nothing but 4 into n in this case. Let's fill this one with 0. We are going with the segment tree to store the maximum heights here. Next, in this case, we'll be going with the lazy propagation array just to handle the range updates. So we have to handle the range updates, right? So for that purpose, we'll be going with the lazy propagation. I'll just give here this dot lazy. This one, let me consider new array of 4 into n. Let's fill this one with 0 initially. This is it for the constructor or the initialization part. I hope this is clear, right? Next step is we'll be going with the update as well as the query functions as we have discussed earlier. Initially, let's go with the update. So I'll just give here update left, right, height s equals 1, equals, let me give here this dot n, and I equals 1. This is fine. We are just going with the update operations. These are the parameters I wanted to consider. Left, right, height, s equals 1. E I have considered nothing but n. We have assigned e to the n. Then finally, I initially we are considering 1. So I'll just write a simple if condition because we have to apply lazy updates before any further processing. So if I can just write in this way, this dot lazy of I. This is fine. After applying the lazy updates before any further processing, what we will do, we have to propagate the laziness to the child nodes, every child node, or propagate laziness to the child nodes. So I'll just write this one and this way. If you don't want to go with the lazy propagation, you don't have to. So this is just for the optimization purpose, right? So I'll just give here this dot tree of I, iterated value of the tree here, this one math dot max of iterated value of the tree, and I'll just give here this dot lazy of iterated value of the lazy. I hope this is clear. Next step, a simple if condition, if s not equal to e in this case. So now let's propagate the laziness to the child nodes step by step. I'll just give here this dot lazy of I into 2. This one equals mat dot max. So I'll just make this one small a. This has to be small a, right? Mat dot max of this dot lazy I into 2. I hope this is fine. And this dot lazy iterated value of the lazy. I hope this is fine. So next we have to do for the another node as well. I'll just copy this one and make the necessary changes, right? So this dot lazy of I into 2, this one will be I into 2 plus 1. This one will be mat dot max of this dot lazy of I into 2 itself. Same thing, plus 1 we have to give here because we are considering two child nodes, right? For every parent, this one parent element, or for every parent element we are considering two child nodes. So this will be same. Let me come out of this one. Finally we have to reset the lazy value. When I say we have to reset the lazy value, I'll just give here this dot lazy, nothing but iterated value of the lazy. We are assigning this one to the 0 here. We are resetting the lazy value here. Next step, let's come out of this one entirely. In this step, what we will do, if the update range is outside the segment range, then we have to just return. I mean, we have to return nothing in this case. We will just give return. That's it. Again, I'm telling, if the update range is, update range is outside the segment range, then we will just give return. So this is simple if condition here. If s greater than r, so in this case, let me give here s greater than r, or I'll just consider one more condition here, e less than l here. In this case, let's return. This is fine. So let me come here. Next, we have to complete overlap. Nothing but we have to apply update every step, right? So again, simple if condition s greater than or equal to l here in this case, and e less than or equal to r. This is fine. We have to complete overlap. I can just articulate that one in the form of code in this way. This is iterated value of the tree. This one equals mat dot max of this dot tree of I, comma h. This is fine. Then next step is, if it is not a leaf, then we have to if it is not a leaf, then we have to propagate to the children. Again, the same thing here. Whatever we have written here in the line number 12, I'll just copy the same thing here. Before this one, what we will do, I will write simple if condition. Nothing but if not a leaf. Not a leaf means s not equal to e, right? Then we have to propagate to the children. In this case, if s not equal to e here, what I'll do, let's propagate to children. I'll just copy the same thing here, paste the same thing. Let's make the necessary changes. This dot lazy of I into 2, this remains same. Mat dot max of this dot lazy of I into 2. Finally, I into 2, this one has to be here instead of, I'll just remove this one. Remove the lazy one. So this one will be I into 2. Till here it is same. We have to include the height here, right? So let me copy the same thing and let me paste it over here. For the children, left node and right node it will be having. So for the right node, we will give here 2 plus 1 again here. I hope this is clear. This dot lazy I into 2 plus 1. This one will be mat dot max of this dot lazy of I into 2 itself. Again, here we have to give I into 2 plus 1 as it is the right node. And we have to include the h here. Why? Because if not leaf, we have to propagate that one to the children, right? Next step. So I hope this is clear. This is it. Next, what we will do, I said we have to just return, if you remember, right? So we'll just return in this case, right? So next, let's go with a partial overlap. We here in this step we went with a complete overlap. So here where this is, just give me a second here. This one is greater than L, this dot tree. This step, we went with the complete overlap till here, right? So next what we will do, we will go with the partial overlap. Nothing but we have to process left and right children. So in this case, I'll just come out of here, return. In this case, what I'll do, let m equals s plus e here. So you can just make use of the math.floor as well. I have just made use of the right shift operator. So both works for the mid here. So we are considering mid, we are calculating the mid here. You can just make use of the math.floor as well, or you can go with the right shift operator as I have used. Both works. So here I'll just give this dot update of, let's pass the parameters L, R, H, height, S, M, finally I into 2. This is fine. So I'll just copy the same thing for another node here. So I'll just give you LRH will be same, mid will be S, S. I'll just delete S. We don't need S here. This is fine. Mid will be mid plus 1 in this case. So mid plus 1, instead of S we will be having E right here in this case. E comma I into 2 plus 1. Let me give here plus 1. I hope this is fine. So the next step here is we have to update the current node with max of left and right child. So this I'll just give here this dot tree of I. This will be math dot max of this dot tree of I into 2, and this dot tree of I into 2 plus 1. I hope this is clear. So let me come out of this one. So next, this is it for the update. So update function. Next, let's write the query function. Nothing but the final function or the query function here. So let me give here query quickly. Let's write this one quickly. So query of what are the parameters I want to pass? X, s equals 1 here, e equals n, nothing but this dot n, as we are going with the class. So I equals finally 1. So these are the parameters I wanted to pass within the query. So first step is we have to apply any pending lazy updates. So simple if condition here, this dot lazy, iterated value of the lazy. Then what we'll do, let's apply any this one pending lazy update. So this dot tree, iterated value of the tree equals math dot max of this dot tree, nothing but iterated value of the tree, and we have to consider lazy as well right here. This one will be this dot lazy of I. So this is fine. So next step is we have to propagate that one to the children. Again, we did the same thing we have for the this one as well within the update as well, right? So again, I'll just copy the same thing, man. I don't want to type this one. So where is this one? Just give me a second here. Yes, no. Here is somewhere we didn't do this one. So this one, yeah, this one. Let me copy this one till here. So I'll just copy paste the same thing here. Yeah, this is if s not equal to e, whatever we are writing here, this one we are just propagating to the children, right? First parent, leaf, then children. So we are propagating this one to the children. This is this dot lazy I into 2 dot max of I into 2, and this one yeah, we have considered lazy itself, right? Not h here. This is fine. 2 plus 1 is not lazy of this is same, this remains same. After this step, what we will do, we will reset the lazy value. This is also same actually to the previous one, lazy of I. We are just this one implementing the lazy propagation here along with the segment tree. That's it, just for the optimization purpose. You can just ignore this one, lazy propagation. If you just want to go with the segment tree, you can just go, that also works actually. So this step, if there is leaf node, then we have to return the height. So this is simple if condition here. If s equals e, then we will return its height. Height nothing but this dot tree, nothing but a iterated value of the tree. I hope this is clear. Next step, I'll just give here, let m equals calculation of mid. So you can just make use of the math.floor. Again here, I'll be making use of the right shift operator. S plus e, right shift operator here, 1. So final step, let's return if x is less than or equal to m, then what we will do, I'll just give here this dot query x s m comma I into 2 here. This is fine. If not, then I'll just give here again. We'll be making use of query x comma mid plus 1 here will involve e I into 2 and I into 2 plus 1, right? For the another node we have to consider here I into 2 plus 1. I hope this is completely clear. So this is it for the update and query. So let me format this one once. Yeah, so first we went with the initialization, second we saw this one update, and third we saw query. Here we have successfully built the segment tree based on the requirement, right? So here let's come to the main function. Initially in the main function, what we did, we initialized the segment tree, and we want to store the result in the resulting array. So we have initialized the result to empty array, and previous height also we need that one. We have initialized this one to the 0. I hope this is clear. So the next step here is we have to process each building and update the segment tree. Every time we have to do this one, right? We have to process each building and update the segment tree. I'll just come here. Let me make use of simple for loop for let what we are considering left, right, and height of this one will be buildings. This is fine. What we will do, segment dot update map dot get of l and comma map dot get of this one r minus 1. I'll just give you a h. So we have made use of the update here, update function from the this one, what do you call, segment tree class, right? So this one, this is fine. Just give me a second here. This one is fine. We are just processing here each building and updating the segment tree, right? After doing this, we have to query the max height of particular coordinate. So to consider each height, I'll just go with let x of coords I have considered, right? COORD, yes. So I hope this is clear. The next step is let's query the max height at this coordinate. So I'll just give you a height equals segment dot, let's make use of the query. We are just querying the max height at the particular coordinate, or at this coordinate we can say here. So I'll just give here, let me come here, let me paste query here. Query, we have to get the value. So I'll just go with map dot get of what value we have to get from the x, right? So this value we need to get. So I hope this is clear. So next step, after querying the max height at this coordinate, what we will do, if the height change, then we have to add the key point to the result. That was the last step in the approach, if you remember properly. So if the height changes, we will add the key point to the result. So here I'll give if h not equal to previous height, then what we will do, I'll just give here result dot push of this one x comma h, and this one will be previous height. Let me assign this one to the height. So if the height changes, we are adding the key point to the result. The final step here is we have to return the computed skyline. So we are saving that one in the result. We have made use of the result variable here, right? We'll just return the result here. So I'll just give here return result. So this is it for the code. Let me format code once and let me hit the run button. I hope this works. Let's see. So here we have the segment tree. So yeah, what happened here? Expected identifier tree. Where? In the line number 54. Let's check the line number 54. Yeah, here this I have left the space. This is fine. Let me run the code again. Hope this works. I have misspelled segment here in the line number 60. Where is this? Yeah, this has to be G, not Q. So again, let me hit the run. Oh, what happened here? Math. So this A has to be small here in the line number 37. Let me quickly come to the line number 37 here. Let me give this one math. So let me hit the run button here. So you can clearly see the sample test cases are getting passed here. So the code works absolutely correct. Let's see. First, I haven't submitted yet, right? Sorry. Let's hit the sub button. I hope this works. Let's see. So yeah, you can clearly see all the test cases are getting passed. So the code works absolutely correct. So we went with basically segment tree with lazy propagation, right? Along with the sorting. So let's quickly discuss the complexities of the code that we have written. So the approach that we went with here is segment tree with lazy propagation and also with sorting. You can clearly see here with sorting. Segment tree with lazy propagation. Here you can clearly see segment tree. We have built this one from the scratch, and every time we are going with lazy propagation inside query as well. Query and update function means we went with segment tree with a lazy propagation. So overall time complexity here would be big O of n log n. Why it is big O of n log n here? Because uh, why it is big of n log n here? Because sorting plays the dominant factor here, right? So this one here you can clearly see we have made use of the sorting here. So sorting plays the dominant factor here. So overall time complexity would be big of n log n. And what would be the space complexity here? Space complexity would be big O of n. Why the space complexity here is big O of n? Because we are making use of the result variable here, and also segment tree, this one here, segment tree array, this one. So overall space complexity would be big of n in this case, right? So the time complexity would be big of n log n, and the space complexity would be big of n. I hope whatever the code that we have written or whatever the solution we have written, that is completely clear. For now, this is it. Thanks for watching, guys.